At exactly 10:18 a.m. on March 28, 2025, a three-man HIMARS crew received the two words they've been waiting for: batteries release. Within seconds, the most sophisticated rocket artillery system ever built would unleash hell on one of Europe's most critical energy facilities, turning a routine morning into a precision strike that would be studied in military academies for decades. The crew had been in position for less than 4 minutes. Their M142 HIMARS platform, mounted on a 6x6 truck chassis weighing just 16 tons, sat perfectly still as hydraulic stabilizers locked the vehicle in firing position. The driver kept the engine running. In less than 5 minutes, they need to move fast to avoid counter-battery fire. Inside the cab, the section chief was making final calculations on the Universal Fire Control System. The UFCS integrates GPS positioning with real-time weather data, ballistic calculations, and encrypted targeting coordinates received through secure satellite links. The system had already calculated optimal launch angles, flight times, and impact sequences for both rockets loaded in the 6-pack missile pod. Two GMLRS rockets sat ready in their launch tubes, each carrying a 200-pound high-explosive warhead designed to penetrate hardened targets. But these weren't any old dumb rockets. Each GMLRS round carries a GPS receiver and inertial navigation system for terminal guidance corrections. With all these redundant systems, each rocket can strike within 15 meters of its intended target, even at maximum range. And despite this capability, the weapon is incredibly simple to operate. Despite carrying some of the most advanced guidance technology ever deployed, the actual firing sequence requires nothing more than pressing a button. The computer handles trajectory calculations and launch timing, and even programs the rockets for time-on-target arrival. Both rounds following different flight paths, but arriving simultaneously for maximum effect. At 10:18, the gunner finally pressed that button. The first rocket roared out of its launch tube with 10,000 pounds of thrust, the massive blast deflector channeling the exhaust away from the vehicle. The HIMARS platform moved backward as the rocket accelerated rapidly upward, reaching 2,300 miles per hour in seconds. 15 seconds later, the second rocket followed. The slight delay was programmed deliberately. Both rounds would follow different trajectories to confuse air defenses, but arrive at the Sudzha gas facility within seconds of each other. The crew was already preparing to move as the rockets disappeared into the morning sky. The driver engaged the transmission while the hydraulic systems retracted the stabilizers. In less than 90 seconds, they'd be racing toward their next firing position, leaving behind only tire tracks and the lingering smell of rocket exhaust. The Sudzha gas processing facility had no idea what was coming next. High above the Russian countryside, two GMLRS rockets were conducting one of modern warfare's most sophisticated terminal guidance sequences. Flying at over 2,300 miles per hour and following carefully programmed flight paths, each rocket was making hundreds of micro-adjustments per second to ensure pinpoint accuracy on a target they wouldn't see until the final moments of flight. The lead rocket had climbed to 45,000 feet before beginning its descent toward the Sudzha facility. At this altitude, the rocket's GPS receiver received crystal-clear signals from multiple satellites, continuously updating its position and comparing it to the programmed target coordinates. But GPS alone wasn't enough for the precision required. That's where the inertial navigation system kicked in. Inside each rocket's nose section, accelerometers and gyroscopes were measuring every tiny change in velocity and direction. This inertial measurement unit, or IMU, provided backup navigation that couldn't be jammed or spoofed by enemy electronic warfare systems. The combination of GPS and inertial guidance meant that the weapons would still find their targets even if Russian forces detected the incoming rockets and tried to jam their GPS signals. The flight paths themselves were carefully calculated to minimize the chance of interception. Rather than flying in straight lines toward their target, both rockets followed terrain masking routes that kept them below radar coverage for most of their flight. The lead rocket approached from the northwest, while the trailing rocket came in from the northeast. Different vectors designed to overwhelm any point defense systems the Russians might have deployed around the facility. With a 60,000 feet per minute rate of descent, the rockets covered the final kilometers to the target in seconds. Russian air defense systems could theoretically engage them, but the combination of speed, low radar cross-section, and terminal guidance made successful interception extremely difficult. As they entered the final 30 seconds of flight, the rocket's proximity fuses became active. Using radar to measure the distance to the ground, each rocket calculated the best detonation altitude multiple times per second. At 10:20, both rockets entered their final guidance phase. The onboard computers were now receiving targeting updates 50 times per second, making minute course corrections to ensure impact on their pre-programmed points. The GPS coordinates locked in their guidance systems weren't random. Someone had detailed intelligence about exactly which components needed to be destroyed to eliminate the facility for good. The Sudzha gas processing facility appeared in their terminal guidance sensors exactly 15 seconds before impact. 200 pounds of high explosives in each warhead were about to demonstrate why the HIMARS has revolutionized modern warfare. Inside each rocket screaming towards Sudzha, 200 pounds of high explosives were arranged in a configuration specifically designed to destroy hardened targets. These weren't simple fragmentation warheads. They were shape-charge penetrators engineered to punch through reinforced concrete and steel like paper. The warhead design starts with the explosive itself, PBXN-109, that detonates at 26,000 feet per second. But it's not the explosive that makes these warheads so devastating. It's how that explosive energy is focused and directed through advanced engineering that turns each rocket into a precision demolition tool. At the heart of each warhead sits a copper liner shaped like an inverted cone. When the explosive detonates, it collapses this copper liner and accelerates it forward at over 30,000 feet per second, creating what's called a shaped charge jet. This jet of molten copper moving at hypersonic speeds can penetrate up to 3 feet of reinforced concrete or 2 feet of hardened steel armor. But the GMLRS warhead goes beyond simple penetration. Surrounding the shaped charge is a fragmentation sleeve containing over 180,000 preformed steel fragments. Once the shaped charge punches through the target's outer structure, these fragments explode outward in a controlled pattern designed to destroy everything within a 15-meter radius. It's like having a precision drill followed immediately by a shotgun blast. The fusing system that sets this off is equally sophisticated. Each warhead carries multiple fuse options that can be selected during mission planning based on target characteristics. For a facility like Sudzha, the warheads were likely programmed for delay fusing, penetrating the building structure before detonating to maximize internal damage. The fuse can delay detonation for up to 0.5 seconds after impact, giving the warhead time to punch deep into the target before exploding. But this isn't the only trick up this missile's sleeve. The GMLRS warheads incorporate incendiary elements alongside the high explosives, magnesium particles that burn at 3,100 degrees Celsius and virtually guarantee the ignition of any flammable materials in the target area. In a natural gas processing facility like this, more than 40 million cubic liters of natural gas flow through its pipes at any given time. This engineering would demonstrate its effectiveness against one of Russia's most important energy facilities in less than 30 seconds, unless Russian air defenses could take them out first. At 10:19 a.m., Russian air defense radars finally detected what was coming. The 76th Air Defense Regiment, responsible for protecting critical infrastructure in the Kursk region, had less than 45 seconds to detect, track, and engage 2 incoming GMLRS rockets, traveling at over 2,300 miles per hour. What followed was a textbook example of why even sophisticated air defense systems struggle against modern precision munitions. The first detection came from an S-400 early warning radar stationed 15 kilometers southeast of Sudzha. The massive rotating antenna, capable of tracking targets at ranges exceeding 400 kilometers, picked up 2 small, fast-moving contacts approaching from Ukrainian-controlled territory. But detecting GMLRS rockets isn't the same as tracking them effectively. The rocket's radar cross-section was deliberately minimized during design. Each GMLRS round presents a target signature roughly the size of a large bird to enemy radars. Their high speed and low altitude flight profile make them extremely difficult targets for the radar operators to maintain consistent tracking on. The S-400's computer systems kept losing and reacquiring the contacts as the rockets maneuvered through their terminal guidance phase. 30 seconds before impact, the Russian air defense battery attempted to engage. 2 48N6 interceptor missiles roared out of their launch tubes, each carrying a 143-pound fragmentation warhead designed to destroy incoming threats through proximity detonation. These interceptors can reach speeds of Mach 6 and have sophisticated guidance systems capable of tracking and engaging multiple targets simultaneously. But the timing was catastrophically wrong. The S-400 system needs at least 60 seconds to develop an effective firing solution against fast-moving targets, and the rockets had been detected with only 45 seconds remaining to impact. The interceptor missiles were still accelerating toward their intercept points when the incoming rockets entered their terminal guidance phase and began evasive maneuvering. The GMLRS rocket's final approach made interception nearly impossible. Each rocket was making micro-corrections every fraction of a second, creating an unpredictable flight path that the Russian fire control computers couldn't predict accurately enough for a successful engagement. The interceptor missiles passed within 200 meters of their targets. Close in human terms, but meaningless at the speeds involved. Making matters worse for the Russian defenders was the dual-axis attack approach. The two rockets were approaching from different directions simultaneously, forcing the S-400 system to split its tracking and engagement capabilities. This classic saturation tactic overwhelms air defense systems by presenting more threats than they can effectively engage simultaneously. 20 seconds before impact, the Russian battery commander made a desperate decision to engage with close-in weapon systems. Two Pantsir S-1 short-range air defense vehicles opened fire with their 30mm cannons, sending streams of high-explosive rounds toward the incoming rockets. The Pantsir systems can fire 5,000 rounds per minute and are specifically designed to engage targets like artillery rockets and cruise missiles. But at 2,300 miles per hour, the rockets covered over 1,000 meters per second. The gun-based systems had fractions of a second to acquire, track, and engage targets that were already beginning their final dive toward the Sudzha facility. The cannon rounds filled the air behind the rockets as they streaked past toward their targets. The Russian air defenses had failed completely. At 10:20 local time, the first HIMARS rocket struck the Sudzha facility's main processing unit. The 200-pound warhead, traveling at over 2,000 miles per hour, punched through the reinforced concrete outer wall like it was made of cardboard. The shaped-charged warhead design focused explosive energy in a concentrated jet that penetrated deep into the pressurized equipment before detonating. The explosion occurred inside the heart of the gas processing system, where compressors maintain natural gas at 75 times the ground-level atmosphere. The blast wave, expanding at 26,000 feet per second, instantly ruptured high-pressure gas lines and destroyed the containment systems that safely contained thousands of cubic meters of natural gas. Pressurized gas began venting into the building's interior within milliseconds at catastrophic rates. But the destruction was just beginning. Exactly 15 seconds after the first impact, the second HIMARS rocket found its mark on the central control building. This warhead was programmed for delayed detonation. It penetrated the building's outer structure and exploded inside the SCADA control room, instantly destroying the computerized systems that could have initiated emergency shutdown procedures. The timing of this double strike was no accident. Military planners had calculated the optimal delay between impacts to maximize destructive effect. The first rocket breached the processing unit and released massive quantities of gas into the atmosphere. The second rocket eliminated any possibility of controlling the rapidly developing inferno. The physics of what happened next were as predictable as they were catastrophic. Natural gas mixing with atmospheric oxygen created the perfect conditions for a fuel-air explosion of massive proportions. The gas-to-air ratio reached optimal combustion levels within 45 seconds of the first impact, creating a volatile mixture that filled the damaged buildings and spread across the entire facility complex. The ignition came from electrical systems damaged by the second rocket impact. Sparking control panels and severed power lines provided multiple ignition sources as the fuel-to-air mixture reached critical concentration. The explosion that followed wasn't just burning, it was detonation, with flame fronts traveling at supersonic speeds and creating pressure waves that shattered windows kilometers away. The blast was visible for miles, a massive fireball that rose hundreds of feet into the morning sky as the facility's entire gas inventory became fuel for an industrial inferno. The sound of the explosion registered on seismic monitoring stations over 100 kilometers away, measuring 2.1 on the Richter scale as the equivalent of 50 tons of TNT detonated simultaneously. Within the first minute after impact, temperatures at the center of the fire exceeded 1,800 degrees Celsius, hot enough to melt steel and turn concrete into powder. The facility's network of underground gas storage tanks began rupturing in sequence, each failure feeding more fuel to the growing fire. 2 precision-guided rockets weighing less than 700 pounds combined had eliminated a facility that had represented decades of construction and tens of millions of dollars in specialized equipment. In less than 5 minutes, years of engineering had been reduced to twisted metal and rubble. The Sudzha gas facility would never again process another cubic meter of natural gas. Bye for now.